right, chapter 4. You guys are working in class on your posters, and we're going to just emphasize a couple things with you that I want to highlight so that you have like a better understanding of it. And so the first thing is, you know, you're looking at the periodic table and reading about the periodic table, and that's not the first time you've probably learned about it. But there's certainly some things on the periodic table you should know. For example, where are the metals located? Where are the nonmetals located? And hopefully you can answer that question at this point in time. And also, for example, where are the metalloids located? Another thing that's important, and some of you have covered in class, but is the idea of, and they just mention it in the book, but it's important, is the idea of the diatomic elements. And there are some elements, many of these elements, you can find just all by itself. For example, carbon. You can find just a carbon atom, but others you can't. And I'm going to highlight these on the periodic table here. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And these are what are known as diatomic. And the word diatomic means literally two atoms. So you'll never find just an atom of hydrogen. You will always find, if hydrogen is by itself, it an H2. Same thing with nitrogen or oxygen. You won't find it just an oxygen atom by itself. Instead, you're going to find an oxygen molecule. It's always found in pairs. Now, you guys, please do not distinguish this, meaning that every time you see an oxygen, it has to have a little 2 after it, because if that were true, this molecule H2O wouldn't exist. We'd have to put a 2 at the end, which, by the way, would make it hydrogen peroxide. So that isn't what it means. It just means if it's by itself, it has to have a 2 next to it. And there's a couple of different ways to remember that. My personal favorite is using the phrase 7 up, because there are 7 diatomic elements, and they form a number 7 on the periodic table. So here's your number 7 on the periodic table, but if you count that, there's only 6. So the last one, you got to look up, and you got to look at the hydrogen, and so 7 up is a good way to remember it. By all means, if you are a Mr. Wood's student, check out, ask him about Hoberfinkel. I know he's a big fan of that, so feel free to do that. There's never fire clean bricks in hot ovens. Again, think about that and see how that plays out. But personally, I'm a big fan of 7-Up because you can just look at the table and see where those diatomic elements are. What we're going to do right now for a moment is we're going to just focus on a particular element. We'll use carbon as an example in order to focus on what we find in the periodic table. And there's a couple things to notice. Of course, there's the symbol and the atomic number and the mass, the atomic mass. So I'm just going to kind of redraw this because I want us to think about isotopes. And when we look at the periodic table and we look at that box of carbon, and it's carbon and you know 6 and it says 12.011, a couple of pieces of information are going to jump out at us. First of all, and I'll get back to this idea of isotopes when I first explain this, we could draw this, and you see this in your book, as carbon 6, and this is a specific isotope. And an isotope being just an atom that has a specific number of neutrons, and there can be varying isotopes, varying number of neutrons. So when we look at this, the bottom number, of course, is our atomic number, which refers to the number of protons in there. And then we also have our mass number. Now, this is atomic mass. That is a different number. This is a mass number, which of course, as you have found from your reading and probably in junior high, this is the number of protons plus the number of neutrons. Well, isotopes have varying numbers of neutrons. So this is one isotope. Oops, that should be of. We could have another isotope, say carbon 13. And while carbon 12 of course, has 6 protons and 6 neutrons. Carbon-13 still has 6 protons, otherwise it would be a different element. But in terms of neutrons, it has 7. Or we could have carbon-14. You've probably heard of radioactive carbon-14 dating. It's a radioactive element, and it also has 6 protons, but it has 8 neutrons. So these are 3 different isotopes of carbon. And almost every element on the periodic table contains mixtures of isotopes. And so the question becomes, well, where did this number on the periodic table come from? And it turns out that if you actually look at how many, like what percentage of the carbon in your body, for example, or in a tree or anything else, you know, for carbon-12, it's like 98.89%. And carbon-13, some of those atoms are like 1.11% of all carbon atoms. And carbon-14 is less than 1% of all carbon atoms have 8 neutrons. Well, when they take a weighted average, counting for the fact that the vast majority are carbon-12, the weighted average is the atomic mass. There's actually no carbon atom that has that mass, but on average, it has that particular mass. All right, so let's look at isotopes, and really I want to just look at 2 questions. I want to think about, well, how are isotopes the same? Oh, let's spell it correctly, though, first. Isotopes, okay. And then I also want you to think about, how are they different? And so when we look at this, certainly, hopefully it jumps out at you in terms of how are they the same. They have the same number of protons. They all have 6 protons. And in fact, if they're neutral, they would have 6 protons and 6 electrons, so that we have no charge. So they could have the same number of electrons in common. But something that a lot of people don't realize is even though they have different numbers of neutrons, they chemically, their chemical properties are the same. One carbon atom acts like another. It doesn't really matter that it has an extra neutron or not. It still reacts in the same way. So its chemical properties are the same. But it certainly has some differences. For example, its mass numbers are different. We just showed that, which therefore means the number of neutrons are different. You can see that up above here. You know, we've got 6 and 7 and 8 neutrons. So those are different. And something else that's different about them is their nuclear stability. As in I mentioned to you that carbon-14 here is radioactive. Can you read that? I'm writing radioactive. Carbon-13 is also radioactive because its nucleus, which is where the protons and neutrons are, isn't stable, and that's what makes something radioactive. Carbon-12, on the other hand, is not radioactive. So even though its nucleus might act differently, they could all react. In fact, the carbon dioxide you're breathing out right now at this very moment, some of it is carbon-14, hardly any. Some of it is carbon-13, a little bit more, and most of it is carbon-12 in the carbon dioxide you breathed out. But the carbon itself acted the same when you ended up eating your sugar and going through the process of respiration and it ended up being broken down. You ended up with all of these carbons in the carbon dioxide you're breathing. All right, I think that's it for now. Tomorrow, back to more poster.